Hello everyone, my name is Pierre Guillou. I work on the TTK library with Julien Tierney at Sorbonne University. Today, I will show you how to extract filament structures with the Morse-Mel complex using TTK. At the end of this tutorial, you should be able to use ParaView and TTK to extract the Morse-Mel complex of any given dataset. The Morse-Mel complex provides information about critical points represented by spheres in the screenshot, and separatrices that link together those critical points and constitute a segmentation of the input dataset. For this tutorial, I will first present some elements of context, then show how to extract features of interest, filaments, and the Morse-Mel segmentation using ParaView and TTK. And first, some bits of context. Astrophysicists use dark matter density simulations to better understand the structure of our universe, and particularly how galaxies cluster themselves. Dark matter filaments between galaxy clusters are called the cosmic webs, and those filaments can be extracted using the Morse-Mel complex. In the chemistry field, researchers simulate the electronic probability density of a molecule from the position of its atoms in space. Here you can see a simulation of the A and T bases from the DNA and how they pair themselves. Chemists are especially interested in locating the covalent and hydrogen bonds between atoms and measuring the steric repulsion effects inside the molecular cycles. In the following, we will focus on a dataset that simulates this particular molecule. I will show you how to use the Morse-Mel complex separatrices to extract the filament structure. Let's hop into the ParaView window. We will open the input dataset file, which is named at.vti, and load it. This dataset has one scalar field which is named density. In fact, it's the opposite of the logarithm of the electronic probability density, meaning that atoms which have the highest electronic density are the minima of this particular field. We can try to understand this scalar field using the surface or the volume representations, but it's quite hard to make something of it. So let's go back to the outline representation, and we will use the contour filter to generate isosurfaces. And one particular isosurface of interest is the one with the value -1, and we'll reduce the opacity of it. So at first, we will extract the features of interest, and for that, we will use ParaView to apply the Morse-Mel complex filter onto the input dataset at.vti. In the first step, we'll uncheck every box except the critical points 1, and afterwards, we will display the critical points using the TTK sphere from point filter applied on the critical points output. Let's do that. Select the at.vti filter, apply the Morse-Mel complex filter, while unchecking every box except the critical points, making sure that the density scalar field is the one selected here. And after 2 seconds on my laptop, the computation has ended, and we can apply the sphere from point filter onto the critical points output. I will increase the radius of these spheres and color them by cell dimension. Here you can see 3 kinds of critical points. In blue we have the minima. In white we have the 1 saddles that are located between 2 minima. And in red we have the 2 saddles that represent the holes into the scalar field. And in fact, those critical points represent the atomic structure of the dataset. Minima are atoms. 1 saddles are the midpoint or the barycenter of the atomic bonds, either the covalent bonds inside the isosurfaces or the hydrogen bonds outside of it. And two saddles represent the barycenter of the steric repulsion effect caused by those molecular cycles. And to extract filaments, we will check the descending one separatrices and the saddle connectors boxes into the property panels, the properties panel of the Morse-Mel complex filter. And then we will use the geometry smoother filter to clean the output of the one separatrices output. Let's go back to the Morse-Mel complex filter. We will check those boxes. We'll run it again. We'll select the one separatrices output and smooth the curves with 100 iterations. And for an improved display, I will use the extract surface and the tube filters to better see what we have. I will color them by separatrix type. As you can see, we have two kinds of separatrices here. In red, we have what we call the saddle connectors that link together two saddle and all the surrounding one saddles from the same cycle. Here, and here. And in blue, we have what we call the descending one separatrices that descends from the one saddles to the surrounding minima. And in fact, those descending one separatrices provide a skeleton of this dataset. And in fact, those descending one separatrices can also be interpreted as the representation of the atomic bonds, either the covalent or the hydrogen bonds between atoms. And last, we will compute a segmentation of the dataset. So we will check the ascending two separatrices box, and we'll clean the output using a conjunction of the tetrahedralized filter and the geometry smoother filter applied on the two separatrices output of the Morse-Mel complex. Let's do that. I will select the corresponding box. The surface have been generated. I will tetrahedralize them, and using the geometry smoother filter to smooth the surfaces. This might take a while, 2 seconds in my laptop. And I will color them by separatrix ID. So, as you can see, those surfaces represent the borders between the area of influence of each minima. In fact, every one saddle between two minima is contained in such surface, in one of these surfaces. And those surfaces provide also a segmentation of the input dataset. And those surfaces can also be interpreted as the area of influence of each atom, the border of the area of influence of every atom in this molecule. So this concludes this tutorial. We have used ParaView and TTK to extract critical points and separatrices of this chemistry dataset, and we got a skeleton and a segmentation of this molecule. Part of this work has been funded by the European Commission through the VESTEC project. So thank you for your attention and have a nice VIS 2020 conference. Bye!